Spring 1945. Soviet armored columns advance through eastern Germany, capturing airfields littered with the debris of the collapsing Third Reich. At an abandoned Luftwaffe base near Berlin, Red Army engineers surround a sleek, shark-like aircraft unlike anything they have ever seen. The Messerschmitt Me 262, Hitler's jet fighter, sits motionless on the tarmac, its swept-back wings and twin-engine nacelles representing a quantum leap in aviation technology. Soviet intelligence had tracked reports of German jet aircraft for months, but now they possess one intact. The aircraft is carefully documented, photographed, and prepared for transport to the Soviet Union for comprehensive evaluation. What Soviet engineers are about to discover will shock them, not because of the aircraft's revolutionary capabilities, but because of a fatal flaw hidden inside those jet engines that doomed Germany's most advanced weapon. The Me-262 represents everything the Allies feared about German engineering genius. Capable of speeds exceeding 540 miles per hour, it can outrun any Allied piston engine fighter in existence. American P-51 Mustangs top out around 440 miles per hour. British Spitfires manage similar speeds. The Soviet Yak-3, one of the fastest Soviet fighters, barely reaches 400 miles per hour. Against the Me-262, conventional fighters are helplessly slow. German pilots who flew the jet described the experience as transcendent, like entering a different dimension of flight, where enemy aircraft seemed frozen in the air. The Me-262 doesn't dogfight. It slashes through formations, unleashes devastating firepower from its four 30-millimeter cannons, then rockets away before anyone can react. In theory, a handful of these jets could dominate entire sectors of airspace. If you're finding this story as fascinating as we do, please hit that like button and subscribe to our channel. We bring you the untold stories from World War II that changed history, and your support helps us continue this important work. Drop a comment below and let us know what other wartime technologies you'd like us to explore. Soviet engineers begin their examination in late spring 1945 at a classified testing facility outside Moscow. The captured Me-262 sits in a hangar surrounded by the best aeronautical minds the Soviet Union can assemble. Some are veteran designers who built the fighters that defeated the Luftwaffe over Stalingrad and Kursk. Others are young engineers eager to understand this technological marvel. The team's mandate is clear: disassemble everything, understand everything, and determine whether Soviet aviation can learn from or replicate German jet technology. The examination begins with the airframe, then moves to the avionics and weapon systems. Finally, the team focuses on what makes this aircraft possible: the Junkers Jumo E-4 turbojet engines. Removing the engine cowlings reveals gleaming machinery of extraordinary sophistication. The Jumo 004 is an axial flow turbojet, a design concept that represents the cutting edge of propulsion technology. Air enters the intake, passes through a multi-stage compressor that squeezes it to high pressure, then enters the combustion chamber, where fuel ignites in a continuous, roaring flame. The expanding gases blast through a turbine section that extracts energy to drive the compressor, then exit through the rear nozzle at tremendous velocity, producing thrust. It's elegant, revolutionary, and represents years of development by German engineers working at the absolute limits of material science and thermodynamics. Soviet engineers photograph every component, measure every dimension, and document the manufacturing techniques visible in the engine's construction. The lead Soviet metallurgist on the team examines the turbine section with particular interest. This area operates under the most extreme conditions inside the engine. Turbine blades spin at 12,000 revolutions per minute, while bathed in exhaust gases exceeding 800 degrees Celsius. The centrifugal forces are immense, trying to tear the blades from their mountings. The thermal stress is equally severe, expanding and contracting the metal with every temperature change. In conventional piston engines, materials experience nothing comparable to this combination of heat, stress, and rotation. Building turbine blades that can survive these conditions represents one of the fundamental challenges of jet engine design. The Soviet team understands this intellectually, but understanding the theory and seeing the reality are different things. The metallurgist removes several turbine blades for detailed analysis. The blades are hollow, an ingenious design that allows cooling air to flow through internal passages, protecting the metal from the worst heat. The manufacturing quality is impressive, precision stamping and welding that creates consistent aerodynamic shapes. But when the metallurgist examines the blade material under magnification, something seems wrong. The metal's surface texture doesn't match what he expects from high-temperature superalloys. He orders spectrographic analysis, a process that will reveal the exact chemical composition of the blade material. When the results arrive 2 days later, the entire Soviet team gathers to review them. What they read explains everything and condemns the Mi-262 program. The turbine blades are made from an iron-based chromium steel, essentially a modified form of conventional steel with minimal alloying elements. Critically, the analysis reveals almost complete absence of nickel, molybdenum, cobalt, and other elements essential for high-temperature performance. Soviet engineers know that their own research into jet engines, still in early stages, emphasizes exotic superalloys for turbine construction. British and American jet programs, according to intelligence reports, use nickel-based alloys specifically engineered to resist thermal creep and maintain structural integrity at extreme temperatures. The Germans, possessing some of the world's most advanced metallurgical knowledge, have built their jet engines using materials barely superior to what might be found in a steam locomotive. The question is obvious. Why? The answer lies in Germany's strategic situation by 1943 and 1944. The Third Reich is strangled by a resource blockade more comprehensive than anything in military history. The British Royal Navy controls the Atlantic sea lanes. The Soviet Union's vast territory is largely beyond German reach after the failure of Operation Barbarossa. Germany's access to critical raw materials depends on a few neutral nations and whatever can be extracted from occupied territories. Nickel, essential for superalloy production, comes primarily from Canada, the Soviet Union, and New Caledonia, all controlled by Allied powers. Germany's pre-war nickel stockpiles are exhausted by 1943, diverted to submarine construction, armor plate, and conventional weapons manufacturing. Chromium supplies are precarious, dependent on imports from Turkey. Molybdenum, cobalt, and tungsten face similar shortages. Dr. Anselm Franz, the brilliant engineer who designed the Jumo 004 at Junkers facilities in Magdeburg, understands the material limitations from the beginning. His early prototype engines, built in 1941 and 1942 with access to proper superalloys, perform remarkably well. Test runs of these early engines achieve 150 hours of operation without major failures. It's not exceptional by later standards, but it's respectable for a brand new technology. Franz envisions further refinement, better materials, improved manufacturing techniques that will push engine life toward the hundreds of hours achieved by mature piston engines. But by 1943, as the Mi-262 program accelerates toward production, the material situation collapses. Franz receives explicit instructions: redesign the engine to use available materials only, no nickel-based superalloys, no exotic elements. Use what Germany can actually produce in quantity. The result is the Jumo 04B production variant, the engine now sitting disassembled in a Soviet hangar. Franz and his team perform metallurgical miracles, developing iron-based alloys that can survive jet engine conditions for brief periods. They incorporate hollow blade construction with internal cooling passages to protect the inadequate materials from the worst thermal stress. They design the engine for rapid manufacturing, using stamped and welded components instead of complex castings that require specialized facilities. They reduce tolerances and simplify wherever possible to maximize production rates. The Jumo ER4B is a masterpiece of engineering compromise, extracting jet engine performance from materials that should not be capable of sustaining it. But physics has limits. The inferior alloys simply cannot maintain structural integrity for long under operational conditions. Soviet engineers understand the failure mechanism after examining multiple engines from different captured aircraft. The problem is thermal creep, a phenomenon where metals deform slowly under sustained stress at high temperatures. When an Me-262 engine operates at full power, the turbine blades experience centrifugal forces trying to pull them outward while bathed in extremely hot exhaust gases. Proper superalloys resist this combination, maintaining their shape and structural properties for hundreds of hours. The German iron-based alloys cannot. Slowly, almost imperceptibly, the turbine blades begin to stretch and deform. The precise aerodynamic profiles degrade. The blades grow longer, reducing clearance with the engine casing. Vibrations increase as the carefully balanced turbine wheel becomes unbalanced. Eventually, elongated blades begin rubbing against the casing, generating tremendous friction and heat. Catastrophic failure follows rapidly. The documentation captured alongside the aircraft reveals the operational reality. Luftwaffe maintenance manuals specify mandatory engine replacement after just 10 hours of flight time for initial inspections. If the engine passes inspection, meaning the turbine blades show acceptable wear patterns, it can be refitted for another 10 to 15 hours. 25 hours represents the absolute maximum engine life before complete failure becomes inevitable. Some engines fail earlier, particularly if pilots demand maximum power during combat. Soviet engineers compare this to their own piston engine fighters. A Klimov engine in a Yak-3 runs for 100 hours between major overhauls. Maintenance crews expect reliable performance throughout that period. The Germans are replacing engines 4 to 10 times more frequently, an operational burden that beggars belief. The Soviet team calculates the resource implications. Every Me-262 in combat service requires a constant supply of fresh engines. For every hour the aircraft spends flying, it consumes 1/10 of an engine's useful life. A pilot flying 2 combat sorties per day, perhaps 90 minutes of flight time total, exhausts an engine every week. An operational squadron of 30 aircraft, if flying regularly, needs more than 100 engines per month just to stay operational. Germany's industrial capacity in 1944 and 1945, under devastating Allied bombing, struggles to produce engines at anywhere near this rate. The result is predictable. Aircraft sit grounded, waiting for engines while pilots grow frustrated, and maintenance crews work frantically to keep any jets operational. Captured German records document the operational paralysis. Jagdgeschwader 7, the first operational Me-262 fighter unit, reports chronic engine shortages throughout late 1944 and early 1945. War diaries show 30 to 40 aircraft assigned on paper, but typically only 8 to 12 actually flyable on any given day. The rest sit awaiting engine replacement, repair, or spare parts that never arrive. Missions are planned with ambitious numbers, then scaled back dramatically when maintenance crews report how many aircraft are actually operational. Sometimes urgent operations are canceled entirely because not enough jets can get airborne. The most advanced fighter aircraft in existence spends most of its time grounded, waiting for engines. The engine problems create tactical vulnerabilities beyond maintenance headaches. The Jumo ER4 is brutally unforgiving in operation. Pilots receive explicit warnings during training: never advance the throttles rapidly. The combustion process in these early jets is delicate, easily disrupted by sudden changes in airflow and fuel delivery. Slamming the throttles forward can cause flameouts where the engine quits entirely, or a thermal shock that cracks turbine blades immediately. Throttle response is sluggish, sometimes taking several seconds for the engine to spool up from idle to full power. This throttle lag cripples maneuverability during combat. A piston engine fighter can go from cruise power to maximum power almost instantly, allowing rapid acceleration and aggressive maneuvering. An Me-262 pilot must anticipate power requirements seconds in advance, making split-second combat decisions impossible. The vulnerability is most severe during takeoff and landing. An Me-262, accelerating down the runway, needs careful throttle management, smoothly increasing power to avoid flameouts or compressor stalls. On final approach for landing, the pilot must maintain enough power to allow a safe go-around if needed, but not so much that the aircraft overshoots the runway. The sluggish throttle response means the pilot is committed to landing once he begins his approach, unable to rapidly apply power if something goes wrong. Allied intelligence identifies this weakness quickly. By late 1944, American and British fighter pilots received briefings on Me-262 vulnerabilities. The instructions are simple and devastatingly effective. Don't chase Me-262s in the air, where their speed advantage is overwhelming. Instead, patrol near known jet bases and wait for them to land. American P-51 Mustangs from the 8th Air Force develop airfield capping tactics specifically targeting Me-262 bases. Pilots identify Luftwaffe jet fields like Lechfeld, Münchenrhein, and Rheine, then orbit at medium altitude just outside the anti-aircraft defenses. They watch the pattern, learning when jets typically return from missions. When Me-262s appear in the landing pattern, throttled back and committed to landing, the Mustangs dive. The jet pilots see them coming but can't react. Advancing throttles rapidly risks flameout or engine failure. The throttle lag means several seconds of helpless vulnerability while the engines spool up, if they spool up at all. Many Me-262 pilots never get their engines to respond in time. They're shot down within sight of their own airfield, sometimes crashed into the runway itself. The Luftwaffe responds by installing massive anti-aircraft defenses around jet bases, creating flak corridors that approaching aircraft must fly through. Batteries of 88 meters, 105 meters, and quad 20 meters guns create walls of exploding metal designed to destroy any Allied fighter attempting to attack landing jets. These flak alleys are dangerous enough that some American pilots refuse to press attacks through them, but others are willing to risk the anti-aircraft fire for a chance at shooting down a jet. The world's most advanced fighter aircraft, capable of speeds that make it untouchable in the air, requires World War I-style defensive tactics to protect it on the ground. The irony is not lost on German pilots, who find themselves dependent on weapons and tactics their fathers might have used at Verdun or the Somme. The engine problems also limit training, creating a vicious cycle of inexperience and losses. With engines in desperately short supply, Luftwaffe commanders must choose between using them for training flights or combat missions. Combat missions take priority, meaning replacement pilots arrive at operational units with sometimes less than 10 hours of jet flying experience. Learning to manage the Jumo 004's quirks, understanding its throttle lag, mastering the speeds and energy management techniques necessary for effective jet combat, all require practice. Pilots without adequate training make mistakes, get shot down, or crash during landing. Each loss represents not just a dead pilot, but also a destroyed aircraft and 2 more engines removed from the inventory. Meanwhile, Allied pilots accumulate hundreds of hours in their aircraft, developing tactics and skills that German jet pilots never have time to learn. Soviet engineers examining the captured Me-262 can see all of this in the aircraft's design and documentation. They recognize the brilliance of the airframe, the revolutionary nature of the jet engines, and the fatal compromise forced by material shortages. Soviet designers are working on their own jet programs, projects that will eventually produce aircraft like the MiG-9 and Yak-15. The lessons from the Me-262 are invaluable. The Soviets understand that jet engine development demands access to high-quality materials, particularly nickel-based superalloys. They understand that engine reliability is as important as raw performance, perhaps more important for operational effectiveness. They understand that rushing a jet aircraft into production before solving fundamental engineering problems creates more headaches than it solves. The broader question facing Soviet analysts is whether Germany's jet program was worth the enormous resources invested in it. The Third Reich manufactured approximately 430S Me-262 airframes between 1944 and 1945. Thousands of UMO-004 engines were produced, consuming scarce materials, factory capacity, and skilled labor desperately needed elsewhere. The program diverted resources from conventional fighter production, bomber production, and ground equipment manufacturing. In return, the Luftwaffe gained a limited number of operationally unreliable aircraft that, despite their technological superiority, never achieved strategic significance. The jets never stopped Allied bombing raids, never regained air superiority over Germany, and never meaningfully altered the war's outcome. Me-262 pilots scored several hundred Allied aircraft destroyed, but this represents a tiny fraction of Allied losses and had no impact on the overall air campaign. Comparing the Me-262 to Allied jet programs reveals the importance of the material advantage. The British Gloster Meteor, entering service in 1944, around the same time as the Me-262, uses Rolls-Royce Welland or Derwent engines built with proper nickel-based superalloys. Initial engine life exceeds 180 hours, with later variants achieving much longer service intervals. Meteor pilots can fly their aircraft aggressively, confident the engines will respond reliably. Maintenance crews can keep squadrons operational without desperate scrambles for replacement engines. The Meteor never achieves the same legendary status as the Me-262, partly because it arrives when Allied air superiority is already absolute, and partly because it's simply more reliable and less dramatic. British pilots fly Meteors on routine patrols, intercept missions, and training flights without the constant drama that surrounds Me-262 operations. American jet development follows a similar path. The United States has virtually unlimited access to strategic materials, including vast nickel deposits in Canada. American jet engines under development in 1944 and 1945 use the finest superalloys American metallurgists can formulate. The focus is on reliability and sustained performance, not desperate improvisation with inadequate materials. When American engineers examine captured Jumo or TO war engines after the war, their reaction combines respect for German ingenuity with shock at the material compromises. One American metallurgist reportedly comments that building a jet engine with these materials is like building a racing car with wooden wheels. It might work briefly, but failure is inevitable. The fact that German engineers made it work at all, even for 10 to 25 hours, is impressive. But impressive engineering cannot overcome fundamental material science limitations. The Soviet evaluation of the Me-262 concludes with the detailed reports sent to Moscow for review by Stalin and the State Defense Committee. The reports acknowledge the aircraft's revolutionary design and recommend incorporating swept-wing aerodynamics and jet propulsion into future Soviet programs. However, the reports also emphasize the operational limitations created by inadequate materials and recommend against attempting to rush Soviet jet programs into production before fundamental engineering challenges are solved. Soviet industry, despite wartime damage and reconstruction needs, has better access to strategic materials than Germany did. The Soviet Union controls vast territories containing nickel, chromium, and other essential elements. With proper planning and development time, Soviet engineers can build jet engines that don't self-destruct after 10 hours. The captured Me-262 itself undergoes extensive flight testing once Soviet technicians install fresh engines and repair systems damaged during capture. Soviet test pilots report that the aircraft handles beautifully at high speeds exactly as German pilots described. The acceleration is breathtaking, the top speed is impressive, and the four 30mm cannons deliver devastating firepower. But the pilots also note the throttle lag, the careful power management required, and the overall sense that they're flying a thoroughbred racehorse with fragile legs. Every flight requires intensive maintenance afterward. Engines are inspected constantly for signs of degradation. After 20 hours of total flight time across multiple test flights, the engines are removed and replaced. Soviet metallurgists examine the used engines and find exactly what they expected: elongated turbine blades, thermal stress damage, and incipient failure throughout the hot section. The engines were perhaps 5 hours from catastrophic failure. The story of the Me-262's engines becomes a case study in the relationship between strategic resources and military technology. Germany possessed world-class engineers, sophisticated manufacturing capabilities, and visionary leadership in jet propulsion development. Dr. Anselm Franz and his team at Junkers achieved genuine breakthroughs that influenced jet engine design for decades afterward. But engineering genius cannot substitute for strategic materials. The nickel, chromium, cobalt, and molybdenum necessary for reliable high-temperature alloys were simply unavailable in sufficient quantities. Germany's strategic position, surrounded by enemies and cut off from global resources, made the material shortage inevitable. No amount of clever engineering could fully compensate. The result was an aircraft that demonstrated revolutionary potential while simultaneously demonstrating the futility of advanced weapons without the industrial and resource base to support them properly. If you've stayed with us this far through this incredible story, we'd really appreciate it if you could leave a comment sharing your thoughts. Did you know about these engine problems before? What other aspects of German wonder weapons would you like us to investigate? Your engagement helps our channel grow and allows us to continue bringing you these deep dives into World War II history. For the pilots who flew the Me-262 in combat, the engine limitations were a constant source of frustration. German fighter ace Adolf Galland, one of the Luftwaffe's most experienced and decorated pilots, commanded Jagdverband 44, an elite Me-262 unit formed in early 1945. Galland recognized the jet's potential, but fought constantly against the reality of its limitations. In his post-war memoirs and interviews, Galland describes the experience of commanding a unit where aircraft are more often broken than operational, where every mission requires careful planning around which jets actually have functioning engines, and where brilliant young pilots sometimes die because an engine fails at the worst possible moment. Galland reportedly told Allied interrogators after the war that the Me-262 was simultaneously the finest fighter he ever flew and the most operationally frustrating aircraft he ever commanded. The human cost of engine failures is documented in Luftwaffe loss records. Multiple Me-262 pilots died or were forced to bail out due to engine failures unrelated to combat damage. An engine seizing at altitude gives the pilot little warning. One moment the aircraft is flying normally, the next a turbine blade fails, tears through the engine casing, and creates catastrophic damage. Sometimes pilots can glide to a landing field on one engine if the failure isn't too violent. Other times, the failed engine catches fire or debris damages critical flight controls, and the pilot has no choice but to abandon the aircraft. Each loss represents not just a destroyed jet, but also wasted training, wasted resources, and another gap in the dwindling ranks of experienced pilots. The engine problem persists until the very end of the war. Engineers at Junkers continue developing improvements, including better alloy formulations using whatever materials are available and enhanced cooling systems. By early 1945, some Yamal Zirori 4 engines achieved 30 to 35 hours of service life, a modest improvement that still falls far short of reliability standards. But by this point, Germany's situation is hopeless. Allied armies advance from both east and west, overrunning jet bases and forcing constant evacuations. Engine production facilities are bombed repeatedly, disrupting output. Transportation networks collapse, meaning engines produced in one location cannot reach aircraft in another. In the final weeks of the war, some Me-262 units abandoned serviceable airframes simply because no replacement engines are available, and the engines currently installed are beyond their service limits. After the war ends, the victorious Allies divide German jet technology among themselves. The United States and Britain capture numerous Me-262s and Jumo ER-4 engines through Operation Lusty, a systematic effort to locate and seize advanced German aircraft. These captured aircraft are shipped to testing facilities in the United States and Britain for comprehensive evaluation. American and British engineers conduct the same metallurgical analyses the Soviets performed, reaching identical conclusions about the material limitations. Some Me-262s are flown extensively for testing purposes, consuming the limited stocks of functional engines. Others are preserved for museums or used as training aids for engineers developing the next generation of jet aircraft. Soviet engineers use their captured Me-262s in technical documentation to accelerate Soviet jet development. The MiG-9 and Yak-15, both entering service in 1946, show clear influences from studying German jet technology. However, Soviet designers avoid the Germans' mistakes. Soviet engines use proper materials, accepting lower performance initially in exchange for reliability. The early Soviet jets are not as impressive as the Me-262 on paper, but they're operationally sustainable. As Soviet metallurgy improves through the late 1940s, subsequent generations of Soviet jet engines become increasingly competitive with Western designs. By the time of the Korean War in 1950, Soviet-built MiG-15s demonstrate that the Soviet Union has not only caught up with jet technology, but in some respects surpassed Western designs. The Me-262 engine story offers broader lessons about military technology and strategic planning. Advanced weapons require not just clever designs, but entire industrial ecosystems to support them. Raw materials, manufacturing infrastructure, trained personnel, logistics networks, and maintenance organizations all must function properly for complex weapons to achieve their potential. Germany in 1944 possessed the first element, clever designs, but lacked increasingly the other elements, as Allied bombing and resource shortages took their toll. The result was weapons that impressed on test ranges but failed operationally. The contrast with Allied weapons development is stark. Allied aircraft like the P-51 Mustang, the Spitfire, or the Soviet Yak-3 were not individually superior to the Me-262, but they were available in vast numbers, supported by robust logistics, and built with reliable materials. 100 reliable conventional fighters proved more valuable than 10 unreliable jet fighters. Modern military strategists studying World War II often point to the Me-262 as an example of how technological superiority alone does not guarantee success. The aircraft demonstrated concepts that would dominate jet fighter design for the next 70 years. Swept wings for high-speed flight, powerful jet engines, heavy cannon armament concentrated in the nose. Every jet fighter flying today traces its lineage in some way back to innovations pioneered on the Me-262. Yet the aircraft's operational impact was negligible because Germany lacked the resources and strategic position to deploy it effectively. The lesson resonates in contemporary military planning. Invest in technologies that can actually be sustained operationally, not just technologies that look impressive in isolation. For the engineers, both German and Allied, who worked on jet propulsion during World War II, the Me-262 program represented both triumph and tragedy. They achieved genuine breakthroughs in aerodynamics, propulsion, and high-speed flight. They pushed material science to its limits and sometimes beyond. They created an aircraft that captured imaginations and influenced aviation development for generations. But they also experienced the frustration of seeing brilliant work undermined by circumstances beyond their control. Dr. Anselm Franz, the UMO-004's designer, worked after the war in the United States, contributing to American jet engine development. In interviews, he expressed pride in what his team achieved under impossible conditions, while acknowledging that with proper materials, the Jumo EO-04 could have been a truly revolutionary engine rather than a brilliant improvisation with fatal compromises. The Soviet engineers who first examined a captured Me-262 in 1945 witnessed a revolution in aviation technology. They saw the future of air combat in the jet's sleek lines and powerful engines. But they also saw the wreckage of Germany's strategic position in those turbine blades made of inadequate steel, in the maintenance manuals specifying 10-hour engine lives, in the operational records documenting chronic readiness problems. The Me-262 taught them that revolutionary technology, without the strategic depth to support it, is ultimately a mirage. Soviet aviation learned from both the successes and failures of the German jet program, building their own jet force on more sustainable foundations. The lessons learned from disassembling those Jumo 004 engines in a Moscow hangar influenced Soviet military technology development for decades afterward. Today, surviving Me-262s are treasured museum pieces displayed at aviation museums around the world. A few have been painstakingly restored to flying condition using modern replica engines built with proper materials. When these restored jets fly at air shows, they demonstrate the performance that made the Me-262 legendary. But the restored aircraft fly with engines that last hundreds of hours between overhauls, engines built the way Dr. Franz originally envisioned before material shortages forced desperate compromises. The restored Me-262s show what might have been if Germany had possessed the resources to match its engineering ambitions. Meanwhile, the historical Me-262s, with their original Jumo 004 engines, remain silent monuments to the limits of engineering genius when confronted with strategic resource constraints. The story of Soviet engineers discovering that Me-262 engines lasted only 10 hours is ultimately a story about the intersection of technology, resources, and strategy in modern warfare. It's a reminder that the most sophisticated weapons are only as effective as the industrial and logistical systems supporting them. Germany's jet fighters represented an enormous leap forward in aviation technology, but that leap was taken from a crumbling foundation. The Third Reich's strategic position by 1945 made sustaining advanced weapons programs impossible. The brilliant engineers who designed the Me-262 and its engines achieved remarkable things with inadequate resources, but they could not overcome the fundamental reality that jet engines require specific materials to function reliably. When those materials are unavailable, even genius has limits. The Soviets, Americans, and British learned from Germany's experience, ensuring their own jet programs had access to proper materials and support infrastructure. The result was post-war jet aviation that fulfilled the promise the M262 demonstrated, but could never quite achieve.